We spent the last few videos solving quadratics, and we're going to take a break from that now to talk about something new. Something that's going to fit real nicely in this chapter, and something that some people like to do earlier, but I think this is a natural spot to put, and it's complex numbers. They're often also called imaginary numbers, which I think is a stupid name, because all numbers are imaginary. It's not like 4s exist in the sense that like we can mine them out of the earth, or there's never a shortage of 7s. So at some level, all numbers are imaginary because they're not tangible. So, we have real numbers. And real numbers aren't really real in the sense that they're not tangible. We can't actually grab them. But imaginary numbers are supposed to be a set of numbers that's non-real. Okay, it's a different classification of number types. But instead of calling them imaginary, it's preferable to call them complex. And complex sounds stressful, which is probably why people avoid it. But the point is, here we go, let's start talking about them. The square root of 25, we know to be 5, because 5 times 5 is 25. Somebody, someday, somewhere, thought, what if there was a square root of negative 25? Wouldn't that be useful? What if I could find the square root of negative 25? Now we know that we've been saying this has no real solution, and I've been really careful to never say no solutions. I've actually said there's no real solutions or there's not any real solution. I've stuck the word real in there pretty much every time I've talked about this. Because there aren't real solutions, but there is an imaginary solution, and by that I mean a complex solution. So somebody said, let's just pretend like the square root of negative 1 exists. Let's pretend like that's a thing. And let's just call that I. And that's kind of I for imaginary, among other things. But I is the square root of negative 1. Now obviously there isn't a real number that when squared gets you negative 1. Like 0.5 or negative 1 or 1, none of those numbers actually work. There's no real solution, no real number, no real square root of negative 1. So we make one up. We call it I. And this actually allows us a lot of flexibility and freedom with mathematics, because sometimes there'll be problems that you'll sort of start and you'll be doing your stuff, and along the way you have to square root something, and that gets you a non-real solution. But then along the way again you square it again and it comes back to real. There are things that are solvable in the end that seem unsolvable in the middle. And to reconcile that, this I was invented. And I'm going to link some videos that are actually super interesting and super informative at a very, basic's not the right term, but a very entry-level degree of complexity for you to watch if you're interested. It explains like where I came from, how it's useful, all these things. But I represents the square root of negative 1. Okay, I think we get that. That means the square root of negative 25 can be thought of as the square root of negative 1 times 25. And we know the square root of negative 1, it's I, and we know the square root of 25, it's 5, so this becomes I times 5, which we then call 5I. In the same way, the square root of negative 16 is 4I, and the square root of negative 900 is 30I. So I'll do some that can't be done so cleanly, like square root of negative 100 is 10I, because the square root of 100 is 10 and the I makes it negative. But the square root of negative 20, well, first thing I'll do is I'll pull out the I. And now it's a square root of positive 20, because I took negative 1 times 20, and I knew the square root of negative 1 was I, so it's I root 20. But now root 20 can be simplified or broken down. That's 4 and 5, and there's a pair of 2's, and the pairs goes out. So this is 2I root 5. That's the simplification of negative root 20. In the same way, negative 44, well, 44 is 4 and 11, and 4 has 2 2's. This is 2I root 11, the I coming from the negative root. Whenever you have a negative square root, you will have an I in there. This also applies to a 4th root or a 6th root or an 8th root. All of these even roots can have I's in them somewhere. Odd roots don't need it, right? The 3rd root of negative 1, well, that's actually just negative 1. Like negative 1 times negative 1 times negative 1 is negative 1. And the 5th root of negative 32, that's actually just negative 2. Negative 2 to the 5th is negative 32, because every time you multiply by negative 2, it goes negative, positive, negative, positive, negative, positive, negative. So the odd roots don't need it, just even roots. Now 210 is prime. I like picking this number because it doesn't look like it's going to be prime, but it is. that's 21 and 5, and that's 7 and 3. So this we would just call I root 210. Some people would say it's 210 root I, but then you have to have the I after that radical, so you have to put this little thing closing the radical to make it clear the I isn't in the radical, which is why I like to put it in front, because that I is not inside that square root. I does this pretty cool little pattern, okay? So I have these written with kind of fancy math form to make it legible, because I want to use these italic I's anyways, you don't care about that. I, we know, is the square root of -1, which we're going to call that I. But I squared, well, that would be the square root of -1 times the square root of -1, since I is the square root of -1. Let's just, remember that. Well, that's the square root of -1 squared. And the squares and the square roots are inverses. This is just -1. I squared is -1. So what's I to the third? Well, I to the third is really I squared times I. It's properties of exponents. There's 3 i's there, I times I times I. Well, it's I times I is I squared. I squared, we know, is -1. And -1 times I is -I. And then I to the fourth is really I squared times I squared. And I squared times I squared, well, we know that I squared is -1, so that's -1 times -1, and that's just 1. So I to the fourth is just straight up the number 1. And now everything will start to repeat. If I do I to the fifth, well, I to the fifth is really I to the fourth times I, and I to the fourth we know is just 1 from here. 1 times I is just I. So I to the fifth is just I. And I to the sixth is I to the fourth times I squared. I to the fourth we know is 1. I squared we know is -1, so that's just -1. By all this same pattern, same logic, it's going to go 1, -1, -I, 1. 1, -1, -I, 1. It just keeps going in this pattern over and over and over, to where if I had something like I to the 87th, well, I could just count out how many groups of 4 does it take to get to 87, because it's going to go, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th. I don't want to count out all the way to 87, but I know at 84, that's 21 groups of 4. So I to the 84th is the same as I to the 4th, because we're counting in groups of 4 now. So I to the 84th is 1. So I to the 85th, 86th, 87th is I to the 3rd. I'm actually going to write you extra credit, or give you extra credit, if you can write a function or a formula to tell us what I comes out to, no matter what the power is. Some students get lost and confused here, and honestly, this power pattern isn't like the most crucial thing we're going to do with I, but it's worth understanding really these two things here. The fact that I to the second power is -1 is terribly important. It comes up a lot. And the fact that I to the fourth just gives you I is how you can restart your cycle. But these I things, they have some pretty interesting properties and methods about using them. So in the past, we've taken a problem like this and tried to solve it. And we had 3 times x minus 5 squared equals -18, and we divide everything by 3, and x minus 5 squared equals -6, and then we try and square root, and we say, ah, shoot, we can't square root a negative number. This has no solutions, no real solutions. Ah, you're right, there's no real solutions, but there are imaginary solutions. Now we can say 5 plus or minus I root 6. Those are the imaginary solutions, 5 plus or minus I root 6. And I'm not going to really delve that far into what this means. There's ways to graph complex numbers, and they're useful with transformations and rotations and all kinds of things. They're actually a terribly important and useful number. In fact, they're considered one of the 5 most important numbers, i.e. pi 1, 0. Those are like the 5 kind of key numbers that all of our algebra is built on and around. And this is the only one that you maybe haven't seen before, and I'm excited to show that one to you someday. But here's I. I is a brand new number. So I'm going to solve this one by completing the square. I'm going to go through it rather quickly. This is actually the exact same video that we had, or exact same problem we had in another video where I said I would come back to it, and I wanted to be a man of my word. Right now, b over 2 squared is 25 over 9. Sorry, nope, that's not correct. b over 2 would be 25 over 6. And 25 over 6 squared is a massive number. This is why I shouldn't go so fast. b over 2 is 5/3. So b over... So I'll calculate b... Okay, Grant, go from here. b is 5/3. Negative 5/3, technically. b over 2 is negative 5/6. b over 2 squared is 25/36. So I'm going to add 25/36 here and here. And I get x minus 5 over 6 squared equals negative 120 plus 25 over 36. So x minus 5 over 6 squared equals negative 95 over 36. If you're wondering where this number came from, it was getting a common denominator with that 3 and that 36 on the bottom, multiplying it by 12. Now I would square root both sides, and last time I said, oh look, we can't square root negative 95, that means there's no real solutions. But now we can say x minus 5 over 6 equals plus or minus I root 95 over 6. Then we add 5/6 to both sides, and x equals 5 plus or minus I root 95 over 6. And when we write numbers in imaginary or complex form, we like to split it up into real parts and imaginary parts. So write it like this. Have the real part first and the imaginary part second. It comes in a form of a plus bi, where a and b can be numbers of any sort, and then I is the imaginary number I, the square root of negative 1. I behaves just like a variable. In fact, it behaves just like a number. It has the properties that numbers have. It can be commuted, associated, it can be distributed with it. We just treat it like it's a variable. So 3 plus 4i minus 2 minus 5i. Well, I'm going to distribute this negative here. 3 plus 4i minus 2 plus 5i. Now I combine my like terms. 4i plus 5i is 9i. 3 minus 2 is 1. It's 1 plus 9i. That's how that simplifies. Leave it split up, so now it's a plus bi, where a is 1, b is 9, I is I. So addition, subtraction, multiplication, division of I is just like with any other variable, except for if you were to do multiplication of multiple i's, well, this would become 15i squared, which is negative 15, because do not forget that I squared is negative 1. So I'm going to multiply these radicals. And this kind of looks like a pain, but I'm going to reduce and simplify everything first. In fact, do I want to do this problem? We're going to hit this problem in a later chapter pretty hard. Nah, let's skip this for now. There's something about I, and we're going to see this later, where we're not allowed to have I on the bottom of a fraction, not in the denominators. We have to multiply by something called the complex conjugate. I'm going to get rid of this I on the bottom of the fraction. So the complex conjugate, what that means is you take the bottom piece, the denominator, and you change the sign in the middle. That's all. You just change the sign. And this conjugate idea is something that will come back again later for us to work with, so understand it now. Now I'm going to do distribution and foiling on top and bottom. I don't like the word foil, but that's what we call it, so I'm going to call it that. On top, 2 times 5 is 10. 2 times 2i is 4i. 3i times 5 is 15i. 3i times 2i is 6i squared. And that can all simplify, because remember, 6i squared is really just negative 6. because I squared is negative 1. So it's going to be 10 minus 6, which is 4, and 4i plus 15i, which is 19i. There's the top of that fraction. The bottom does something terribly magical and wonderful. This is going to be a difference of squares. 5 minus 2i times 5 plus 2i. Because 5 times 5 is 25. 5 times 2i is plus 10i. Negative 2i times 5 is negative 10i. And negative 2i times 2i is negative 4i squared. These two things cancel. 10i minus 10i is 0 because they're opposites. So it becomes 25. And then negative 4i squared. Well, I squared is negative 1. So this is actually plus 4. 25 plus 4 is 29. We have this. We got rid of the I on the bottom of the fraction by using the complex conjugate. That's how you simplify these. You have to multiply by the conjugate, and the beauty of this method is these middle terms will always cancel. So if you have something like this, well, I don't want to use A, I'll use like, I don't know, D. D over A plus BI will always become D times A minus BI over A squared plus B squared. Those things always get multiplied and squared, and it's a positive because this plus here and this minus here combine to get you a negative, then the I squared combines to make it a positive, so it's A squared plus B squared. That's your formula if you want a formula, but you don't have to follow it. If you don't have a binomial on the bottom, it's just a monomial with one term, it's actually much simpler to get rid of the I. You just multiply by I. So now we have negative 6i plus I squared over 3i squared. Let's remember that I squared is negative 1, so it's negative 1 minus 6i over negative 3. And I don't like having negatives on the bottom, and this has a negative everywhere, so divide everything by negative 1. 1 plus 6i over 3, and then we split it up. 1/3 plus 2i. If you didn't quite follow that, I did this. That says 6i right there. 6i over 3. And then 6i over 3 is just 2i. So now I'm going to sneak in here real quick and show you how you can use your calculator to do all this I stuff. If you type the square root of negative 1 into your calculator, it's probably going to say error, non-real answer. Whenever it gives you an error, you should actually read what the error is. It's trying to tell you how to fix it. And if you click quit, it just stops. But go to can take you to where the problem is. It's saying, okay, at the end of this statement, I tried to do some math and I couldn't do it. Let's go fix it, Mr. User. Well, the problem is, if you press this mode button right here, the calculator is set up to be in real. It's only working with real numbers. But if you jump over here to A plus BI, now it'll give things to you in imaginary numbers. And so now if I do the square root of negative 1, I get I. And if I do second period or decimal point, if I second that button, that's just I. So I can find I squared. Oops. I squared is negative 1. And if I do this problem here, negative 6 plus I over 3i. Well, first of all, the top part has to be in parentheses. Don't ever forget that. Of all fractions, the tops and bottoms should always be in parentheses because the big fraction bar is like a grouping symbol. So I'm going to divide this by 3i. Negative 6 plus I divided by 3i gets me 1 plus 2i. What did we get when we did this? Oh, well, there wasn't a 3 here. Shoot. Okay, there was no 3 here, so let me change this. If I do second enter, that pulls up my previous answer. I'm going to go back and delete that 3. And now we get 1/3. 0.333 repeating is 1/3 plus 2i. 1/3 plus 2i. If I want this in a fraction, math, arrow frac, 1/3 plus 2i. So yeah, I'm not just making all this stuff up. Okay, I is an actual number. It's the imaginary number. It's the square root of negative 1. It's incredible. Okay, I'm going to go over more examples, and if you feel like you don't need more examples, then I think you're good at this point. So let me say before I do that, I is actually the basis of our electrical grid. Things that go negative, negative, positive, positive, you know, that's how that I squared, I to the third, I to the fourth, it technically went positive, negative, negative, positive. That positive-negative switching that it does is very, very useful for the mathematics of charges and the mathematics of electricity. So this is what's so great about mathematics. You might see something like I and think, gosh, that's annoying. They can just make stuff up. Things that don't even make sense, things that aren't even real. And then all of a sudden say, hey, look, we can have I now. I is a thing. Why can't we have imaginary everything else? Like, say, we know 3 plus x cannot equal x. This is an unsolvable problem. Can't we just say, let's just say x equals plus, and plus is my imaginary number, and now it's solvable. Well, it turns out, if we just make up something like plus, it doesn't follow any logical, coherent structure of rules that make it useful. It's just literally nonsense, whereas I has all the properties of other numbers. It can be distributed, it can be associated, it's got all the requirements that these numbers have for them to be of value. But the real beauty of math is you can take something that seems unsolvable and then just make something else up. I'm going to be solving this problem where I talk about how wonderful this is. Just make something up in hopes that it works, and then see if it actually works. And when it does, you can change the world, right? I is an incredibly important and useful idea and an important and useful term that didn't exist until people thought, maybe this should exist. Things don't happen like that in too many places besides mathematics. Mathematics is one of the only places where you can just sort of like imagine something to be true and then make it true. There have been so many times where I've said, okay, so A isn't 1, want to make A 1, let's just make A 1. Well, you can't just make things, other things, automatically in your life, right? Like if you want to be stronger, you have to work really hard. And if you want to be richer, you have to work really hard or get really lucky. And if you want to be prettier, you have to be rich already, or work real hard, or get lucky, or maybe you just can't. And if you want to be taller, you just can't. Like, things in life you can't just get. But with mathematics, when you want something, you can get something. That's awesome. It's exciting. And I know you don't really care right now. You know, a lot of you are like, stop talking, please just solve this. You're not even explaining what you're doing, and it's not helpful. Okay, sorry, but I hope you understand. There's some real value to the freedom that comes with math. A lot of people don't think of it as a freedom. They think, I think math is a bunch of rules you have to follow, and if you don't follow, you get things wrong, and that's just stupid. But it turns out, where there's rules, there's freedom. As long as you follow the rules, you can do whatever you want. Right? You ever think about that? As long as you follow the rules, you can do whatever you want. So if a few things are made really, really clear, like when you're a kid it was, don't touch things that are hot, and don't cross the street, and you've got a few rules to follow, but if those rules were defined well, and if they were sufficient, if they covered the right amount of things, everything else was more or less fair game. Well, that's how it goes with math. We have a lot of really clear, really precise, very specific rules, but once you follow those rules, you can do whatever you want. And the nice thing about those rules is they weren't just made up. They're not just arbitrary little things that we're doing to make you mad. They're necessary through logic. That's just how logic works, and that's therefore how math works, because math is the language of logic, which makes it the language of science, which makes it the language of the universe, and what governs the universe, and how could you not want to learn this? Rant over.